The XF-92A Convair Model 7002 is a research airplane, a part of the XF-92 program. It is presently being flown at the U.S. Air Force Base, Muroc, California. The purpose of these flights is to gather data concerning the characteristics of a new configuration designed to meet the requirements of an interceptor fighter operating at transonic and supersonic speeds. Extensive study and research by Convair engineers some time ago led to the conclusion that the best aerodynamic configuration for this type of operation was one utilizing a 60-degree delta wing. The wing planform promised several major advantages. First, low drag at transonic and supersonic speeds. Second, smooth handling characteristics and freedom from buffeting at transonic speeds. Third, satisfactory low-speed handling characteristics. And fourth, a structural form ideal for attaining high rigidity, lightweight, and simplicity. Numerous tests of models in wind tunnels and in free flight have confirmed these conclusions. Full-scale confirmation, however, is essential. The Model 7002 airplane was constructed to obtain these full-scale data. It has a 60-degree delta wing and a similar vertical surface. The airplane is powered at present by a single J-33A-23 jet engine with 5,400 pounds thrust for takeoff. Although this is less thrust than is obtained from more recent power plants, it does permit exploration of the airplane's characteristics at high subsonic speeds in level flight. Still higher speeds are obtained in dives. To establish correlation between theory and practice for this new wing planform, a flutter study is being conducted as a part of the program. A major problem in the design of all aircraft capable of transonic speeds is that of providing satisfactory control forces. The 7002 utilizes a 100% hydraulic boost system with no feedback. The pilot senses stick forces which are produced by an artificial feel system. Forces are made to vary automatically with airspeed. Pilot comments during flight tests are taken on a wire recorder. An oscillograph and movie photo panel installed in instrumentation compartments comprise the other principal means of recording test data. Perhaps the most outstanding characteristic of the 60-degree delta wing is the low drag rise encountered at transonic speeds. A comparison of the increases in drag coefficient of conventional swept-back wings and that of a 60-degree delta wing near Mach 1 is presented here. The maximum value of the drag coefficient C sub D for the conventional wing is approximately 4 times that of the delta wing. Even more significant is a comparison of thrust requirements in the transonic and supersonic speed ranges. It will be noticed that the difference in speed between the 35-degree swept wing and the 60-degree delta wing is small at the lower values of thrust. However, at the higher thrust, representative of future power plants, the advantage of the delta wing becomes very impressive. Airplanes with conventional tail configurations experience a reduction in elevator effectiveness on approaching Mach 1, whereas a delta wing with integral control surfaces does the opposite. This means that the maneuverability of delta wing aircraft will not be objectionably diminished at transonic and supersonic speeds. Another advantage of the delta wing is that gusts produce lower structural loads. Presented here in graphical form are comparisons of the effects of negative and positive gusts of 2 intensities. Flight at supersonic speeds with the best turbojet power plants now being developed is practical only when wing thickness ratios are 5% or less. At 5% thickness, the wing weight per square foot of a delta wing is less than half that of a conventional wing with sweepback. Simplicity of construction inherent in the delta configuration is demonstrated by a comparison of the aerodynamic control surfaces required. The controls in the pilot's compartment are conventional. Elevons form the wing trailing edge and move up and down together to produce elevator action when the stick is moved fore and aft. When the stick is moved from side to side, one elevon moves up, the other down. This provides aileron action. Pedals control the rudder, which operates in conventional manner. Initial flight of the 7002 was made at Muroc Air Force Base in the latter months of 1948. In such testing, precise scheduling of operations is required. Other test projects utilize the same facilities. Coordination of all test activities is performed by the Air Force. Before the airplane is taken from the hangar, film is inserted in the instrument recording cameras, batteries are charged, and numerous other items are serviced or inspected. In order to have full tanks for flight, the airplane is towed to the runway before the engine is started. The pilot, flight inspector, and other project personnel necessary to the performance of a flight leave for the runway. Air-to-ground radio communication is maintained throughout test flights. A radio truck receives and transmits pertinent information to observers spaced along the runway. Wind velocity and direction are measured immediately before takeoff. Prior to the first extended flight, a number of high-speed taxi runs and straightaway flights just off the runway were made to provide data for adjustment of the control sensitivity. Allowed the pilot to become familiar with the airplane's handling characteristics and to develop the technique of flying at the high angles of attack associated with low aspect ratio wings. The first tests were conducted on the 7-mile lakebed runway. Subsequent flights have been carried out from time to time on the main concrete runway and the shorter lakebed runways. The combined efforts of the Air Force, the NACA, and Convair have been devoted to the launching of this new type aerial weapon. First takeoff is uneventful. A chase plane is used to make close-up visual and photographic observations of the airplane and its behavior in flight. The two pilots maintain contact by radio. Movie cameras within the fuselage record control movements, airplane attitude, throttle setting, speeds, pressures, temperatures, in short, every aspect of the flight. Approximately 1,500 pounds of instrumentation is carried. This represents more than 10% of the airplane's gross weight. The gross weight at takeoff is about 13,500 pounds. The fuel burned in a 30-minute flight reduces the weight to 12,000 pounds for landing. Completion of the first flight marks the beginning of a period of adjustment, calibration, and research testing. Records must be removed, reproduced, and studied before another flight. The study, planning, and preparation of instrumentation for each flight takes much more time than the operations connected with flying. Limited tests to date show lower drag and higher performance than predicted. Difficulties encountered up to the present time all appear to have reasonable solutions. No problem has yet arisen which compromises the basic advantages of the delta wing configuration. This airplane is the one design now flying in which a pilot can operate transsonically with no undesirable aerodynamic disturbances. With the inherent low drag and good aerodynamic characteristics at transonic and supersonic speeds, the Air Force now has a weapon which can be developed tactically with confidence.